Hey everybody, and welcome back to Algebra 2 Online. So today marks the start of like a new unit, but it's kind of not so new at the same time because we've seen these things before. What we really haven't seen is the graphs of them, so that's kind of the big part that I'm going to be stressing. So the new unit is called rational functions, and really they're just any functions that pop up in math where you have a function of x on top and bottom. So basically there's like a ratio involved, right? And like we've seen things like this in our last unit. This is might have actually been one that I asked you to find like the domain of in one video previously, but we never really looked at what they look like because they look kind of weird. They look like this. That's actually this graph. So to start off, I just want to do the domain part that we've kind of done before, but then connect it back to this picture. So I don't expect you to know this picture yet, but kind of after the next few videos, we will be able to know how to graph this. So for the domain of this thing, right, one part is that we could be dividing by 0. And so we need 2x minus 3 to not equal 0, right? So we need 2x to not equal 3. We need x to not equal 3 over 2, right? That's going to be one part. And actually, we can put that in the picture. So what we're going to find in this unit is that there's these vertical asymptotes. And they're basically a line that the graph gets really, really, really close to, but doesn't touch. And there's one here at x equals 3/2. So that's one of them. The other thing, right, that can happen is you need the inside of any of these even roots to be greater than or equal to 0. So I'm just going to add x over, right, and then I'll be done. So it's saying that x needs to be less than or equal to 2, all right? And so you can see that, right? Here's 2, right? And we're, to the left of 2. There's no parts of the graph that are to the right of 2. And so that's the connection between the domain and the picture. Now, you don't know this, I don't expect you to know this yet, but there's actually a horizontal asymptote, okay? And the horizontal asymptote in this one is going to be y equals 0. And you're going to learn about why that asymptote appears there in a later video, and all sorts of stuff. But eventually you'll be able to kind of put together all these different things that you know about it and actually get a pretty good sketch of what this thing looks like. So I want to start off with, honestly, the most basic rational function you could have, and that's just 1 over x. So this is what 1 over x looks like, and actually we saw it way back in that Desmos project that we did in like September or something like that. So the domain of this graph, so what's going on, let me just kind of explain a little bit here. So the graph, continues getting closer and closer and closer to these kind of invisible lines, which actually do happen to be on the x-axis and the y-axis here. But you can also just get the domain by looking at this, right? There's only one number in the world that you can't include in this function, and that's when the bottom is 0, right? So the domain in this one is all reals, but x cannot be 0, okay? And as we see when we look at the graph, as x goes way out to infinity, right, we can see that the function value, the output, goes to 0. As we go to negative infinity, this way, right, likewise, we can see that the output value goes to 0 again, right? We're getting closer and closer and closer to the x-axis. As x goes to 0 from the positive numbers over here, right, you can see that the function value skyrockets. It's going up to infinity. But if you came in from the other side, if you came in 0 from the negatives, right, you can see that it goes to negative infinity. And that makes sense if you start thinking of certain numbers, right? Like if you plug in 1 over negative 100, actually let's even just do 1 over negative 10, 1 over negative 100, 1 over negative 1,000. So basically what I'm doing is I'm increasing the order of magnitude on the bottom here. So if you think about the progression, right, as you plug in bigger and bigger and bigger negative numbers, right? This thing is getting more and more and more, right? So the, 1 over a huge number is basically 0, and that's why, like, as you go out to negative infinity, the function value will approach 0. It approaches it from below 0, right? Because these are negative numbers. If I did the same thing, but I did it with positive numbers, right? Then I would be approaching 0, but from positives. So that's how I'd get that. And then if you did, if you mixed it up a little bit, and you plug in increasingly smaller numbers, right? So if you did 1 over 100, and then 1 over 1,000, and 1 over 10,000, let's say. So this one would be, you'd flip that around, and this would be 100. This would be 1,000. This would be 10,000. And so you can see here that you're skyrocketing, right? As you approach 0 from the positives, the thing is shooting way up to infinity. So this is a very important rational function. Now, it's kind of like, but it's one of our parent functions that you're going to want to know. We're going to use it to help us graph today. So a very similar graph is 1 over x squared. This one, really what it just does is it takes, before we had 1 over x here and here, and if you're squaring the x numbers, right, any of these negatives would get squared and they would like sort of pop up right here, right? And so we get something that's very similar to 1 over x, but it's kind of, it's very similar to if you have y equals x, kind of think of that as the last example, and now we're thinking y equals x squared. It just takes, y equals x would look like this, and y equals x squared sort of takes that and pops it up. Now, it does do some curvature changes, obviously. We know x squared is a curve like that, but that's, it is functionally a little different than here. But, and actually the curvature change is reflected also in there. But the basics on this one, the domain, still the same thing. X just can't be 0, but you can have all of R besides that, right? It just comes from this piece right here. You don't want to plug in 0. And as we go out to infinity, right, x goes out to infinity, we can see that f of x goes to 0. As x goes to negative infinity, right, the function value is also going to 0 still. And as you go to 0 from the positives, you can see that the function value skyrockets. And then again, as you approach 0 from the negatives, you're going to go to positive infinity still because, you're squaring a negative number and it's making it positive. So these become our kind of two building blocks for graphing rational functions. The same way that like we sort of know that even polynomials end in the same direction, even rational functions, like anything that looks like 1 over x to the 4th, 1 over x to the 6th, 1 over x to the 8th, all of these sort of look like that one. Whereas your odds, your 1 over x, your 1 over x cubed, your 1 over x to the 5th, ... all of those look like that thing. So when we graph and we make a sketch, all that needs to happen is that it needs to be kind of a rough sketch based on these two parent functions. You'll just use this one or you'll use this one. And if it's odd, you base it off of that one. If it's even, you base it off of that one. So let's do a few of these. So using what we just saw here, I just want to sketch -1 over x plus 2, and then all of that stuff plus 3. So what we're basically doing, we got an odd rational function. So there's sort of these imaginary lines that we're not crossing. And this would be, I'm doing a horrible job sketching this. So this would be what 1 over x looks like, and that's what we're going to base everything off of here. So using function transformations, we can do this one of two ways. If we want to do the negative, negative would just flip, okay, right? It's a vertical flip. So then we would take our parent function 1 over x, and now this part would pop up here, and that part on the right would pop down here. So that is negative 1 over x, right? So I'm going to get rid of this as I go here. And then we can do the shift. So the plus 2 acts as a, that's inside the function. And, the function is the 1 over x part, so we're on the bottom, so that's inside this type of function. And plus 2 moves it left 2. So we take, what graph we just had, and we move it over to left 2. So everything's going to shift. So, this vertical asymptote is going to move over here. And then this horizontal is going to move, left 2, but it's infinite, so that'll just kind of stay put. And so then I use those as my sort of guide to tell me where the function goes. So it's going to be kind of in there and in there, right? And then I'm going to delete, so that one is negative 1 over x plus 2. So now I'm going to delete everything I don't need. All right, I had to delete the whole thing. So that is negative 1 over x plus 2. And then the last one, we know that plus 3, it's on the outside. That's going to be a vertical shift up 3, right? So this one would affect the horizontal asymptote, right? The horizontal asymptote is going to go up to 3, right? But then the vertical asymptote wouldn't move anywhere. And so we would basically just be in that region there, or in that region there. And again, I'm going to delete some stuff to make this read a little better. So the takeaway for graphing these things, what I basically would do is, if I give you one in this form, the plus 3 is going to affect the horizontal asymptote, right? So that part dictates that the fact that horizontal asymptote is going to be up at 3. And then the plus 2 is, going to move the vertical one to left 2. So you're going to be over here. And then you're going to just get this kind of, it was an odd rational function. So you're going to get the kind of structure of this one. But we also know that there's a function transformation of a negative. So we have the vertical flip going on. So that would be kind of what I would expect for the sketch of this thing. So I want to do one now with an even, all right? And I'm going to do this one a little quicker. So what we're basically doing is we're basing it off of, the parent function 1 over x squared. So that one is sort of where you're starting from. And just going through the transformations here, we can see minus 3 inside. So that's going to be a shift to the right 3. And then this negative is also inside. And so that we know as a horizontal flip, right? And then minus pi is down pi. So one of the things that's pretty nice about this problem is whenever you have, this negative, for something, so that negative is horizontal flip, right? So if you have a function that is symmetric with the y-axis, right? Just like x squared, right? If you flip x squared and you do negative x squared, it still equals just x squared, right? It's like this part is flipping over here, but then this part flips over here, and you get the same graph. So this, even though that's there, it ends up not really playing a role, right? So the graph of this will actually be the same as the graph of that. And so that's really what I'm going to basically use now. So based off of this, I'm going to shift it to the right 3. So that would affect the vertical asymptote. So the vertical asymptote is going to be at 3. And then the minus pi is shifting it down. So it's a little bit past 3. That right there. And then, there's no vertical flips or anything going on, so we basically just need to draw a curve that gets close there and there, just sort of based on the structure of this. And so that would be the sketch that I would expect for this. You don't need to know exactly how curvy the whole thing is. That part can be kind of tricky. Really, that would be the same graph I would expect for one, like if that was to the 4th or to the 40th or whatever. Any even power will basically have that structure. So I'm fine with like just showing a curve in there like that. So the last thing I want to do is just actually something we did a long time ago. So we've seen rational functions like this, I think for the first time when we studied quadratics. And what we never saw was those graphs of them, okay? And I might show the graph of this in class or something. It's a pretty weird graph, okay? But for solving equations with them, due to that weird shape and the fact that like there's like undefined spots and things like that, we often need to be really careful about our answers. Sometimes we solve it all out and it looks correct, but then our answer is actually not correct. So the way we did these things before was we started by like factoring the thing out, okay? So anything you can factor out, just factor. So basically I'm just like simplifying. So I could take a 5 out of this. Nothing I can do to that second one. The bottom one we can factor into x plus 2 and then x plus 1. And so at that point, then you can look at the bottom and see what is the common denominator that you could multiply everything by and cancel out all the fractions, right? That was kind of our first step when we did these. And so you have an x plus 1, right? You have an x plus 2, and you got a 5. So if you just multiply this whole thing by 5 times x plus 2 times x plus 1, right? You should cancel off, when you distribute that, you should cancel off all the bottom. And then it's going to turn into a much nicer problem. So, when I do this first one here, right, 5 and 5 cancel, and x plus 1 and x plus 1. And so I would get x times x plus 2. Then, when I do this one, the x plus 2 and the x plus 2 cancel, and so I would just get, 5 times x plus 1. And then the last one, it cancels this and this, but not the 5, so you have like a plus 5 there. And then it's a problem that you can just like multiply, distribute everything out, and oftentimes these things turn into quadratics. So if you just move everything to like the left, you're going to get x squared minus 3x minus 10. And then that thing factors, x minus 5, x plus 2. So it's looking like x is 5 and negative 2. But you got to be careful. So, if you look at this one, right, if we plug negative 2 in there, negative 2 is where it equals 0 on the bottom. And that's where you're going to get like a vertical asymptote like that. So negative 2 doesn't work if you, and if you check 5, right, 5 plugged in, you really only need to check it on the bottom. If it works in the bottom everywhere, then it's going to be perfectly fine. 5 times 5 plus 5, that's not 0. 5 plus 2, definitely not 0. And then here also, if you do 5 squared plus 3 times 5 plus 2, not going to be 0. So this thing definitely works, okay? But we will actually have a day where we just solve these things out, and that's basically how you do it. You find the common denominator, you multiply every term by that, you should then kill off the fraction, and then you'll just solve whatever polynomial you got. And you just have to be careful that you got to remember to check your answers, because these rational functions are not defined everywhere. All rational functions have some sort of undefined thing going on, some sort of domain issue, because you're dividing by 0 somewhere. So that is about it for the kind of intro to rational functions here.